Welcome to our materials science lecture on stress-strain curves. Today, we will explore the fundamental concepts of stress and strain in materials. By the end of this class, you will be able to measure 6 major properties of metals from a stress-strain curve and explain elastic deformation with E, the elastic modulus. Elastic deformation is linear and reversible. On a macroscopic level, bonds stretch and return to their initial state when unloaded. Different materials have varying elastic moduli. Ceramics have the highest, followed by metals, and then polymers. Yield strength is the stress at which noticeable plastic deformation occurs. It is determined using a 0.2% offset method. At the yield point, bonds stretch and planes shear, causing permanent atomic displacement. This marks the transition from elastic to plastic deformation. Comparing yield strength across materials, metals generally have higher values than ceramics, polymers, and composites. Let's calculate the elastic modulus and yield strength from the given stress-strain curve. Using the stress-strain curve, we calculate the elastic modulus to be 10 gigapascals. Next, we determine the yield strength using the 0.2% offset method, which gives us 22.5 gigapascals. Tensile strength is the maximum stress on the stress-strain curve. Metals strengthen as strain increases, while polymers break at maximum strain. Ductility is the percentage of elongation at failure, representing irreversible work without material failure. Ductility can also be measured as the percentage reduction in area after cold rolling. To calculate the percentage reduction in area, we use the initial and final dimensions of the material. Let's apply the formula to calculate the percentage reduction in area for a US penny after rolling. Toughness is the total energy absorbed at failure, combining both elastic and plastic work. The 3-point bend test measures the flexural strength of brittle ceramics, providing typical values for various materials. Approximate the amount of elastic and plastic strain at failure using the stress-strain curve. From the stress-strain curve, we find the elastic strain to be 0.20 and the plastic strain to be 0.52. Let's recap the learning objectives: measuring properties from stress-strain curves and explaining elastic deformation. Revisit the activity to calculate the percentage reduction in area for a US penny using given dimensions. Thank you for watching. Please like, share, and subscribe. Comment below with your thoughts and what you'd like to learn next. This presentation contains copyrighted material used under fair use for educational purposes. Links to resources are provided in the video description.